Imagine trying to push water through a garden hose. Let's say this hose is wide and smooth and allows water to flow easily, but if you pinch the hose down, suddenly it becomes much harder for the water to get through. Electricity behaves surprisingly similar. In a circuit, current wants to flow, but resistance determines just how difficult that journey would be. By the end of this video, you will have a solid understanding on what resistance is, along with formulas to further understand its impact on the circuits. Okay, so to start off, I think the appropriate question to ask is, what exactly is an ideal resistor? An ideal resistor is a circuit element with the property that the current through it is linearly proportional to the potential difference across its terminals. So that means that if the voltage were to increase, then the current increases, and vice versa. So if the voltage decreased, the current decreased. And the voltage is basically the pushing force applied onto the electrons, resulting in the flow of current. A group of formulas known as Ohm's law is commonly used to understand a circuit's behavior and their current to voltage relationship. So we kind of already know what I and V represent, where that's the current and the voltage, and they're measured in amperes and volts. And here we're going to introduce actually two new variables, being the resistance, which is the variable R and is measured in ohms, along with the conductance, and that's given the variable G and measured in Siemens. And that's basically just the reciprocal of the resistance. Here we have the symbol commonly used in wire diagrams to represent a fixed resistor from point A to B, and you tend to have either the variable R or an actual resistance value displayed in ohms. Regarding the value of resistance, this is primarily determined by the physical dimensions and resistivity of the material of which the resistor is composed of. As we break down this formula, let's take a simpler approach and imagine we have a bar of resistive material of length L and a cross-sectional area A. The resistance can be calculated by taking the resistivity of the material multiplied by the length of material divided by the cross-sectional area, and that is equivalent to the material length divided by the material's conductivity multiplied by the cross-sectional area. So that implies that the conductivity of the material is the reciprocal of the resistivity. And that was kind of shown previously, where conductance is the reciprocal of the resistance. The table includes several common materials and their resistivity. Here we have conductors, which are very common and have very low resistivity, like silver, copper, and gold. And we also have several insulators, like rubber and polyester, which are very high in resistivity. The resistor is manufactured in standard values with various resistance tolerances, several power ratings, and in a number of different methods of construction. There is a standard color-coded band system used for evaluating resistance for particular resistors, where the bands may be indicating the resistance of the resistor, a multiplier, or even a tolerance for the resistance. And that's what's shown in the table here. It's not expected to be memorized, but it's a good kind of visual and understanding. And once you have a good approach towards this, you can identify any resistor that you're given based on the construction method. So let's say we were given a resistor and we didn't know exactly what that resistance value was. We didn't have an ohm meter on us to digitally display the exact value. And let's say the resistor that we are given has 4 bands as shown on the right. And these colors from left to right are red, red, orange, and black. Now looking at the table, red being the first and second band implies that the digit of the band would be 2 and 2, and the third band being the multiplier, and that color is orange, implying that it is 10 to the third. And lastly, we have our tolerance band, which is black, so we have a tolerance of 20%. And I have the plus or minus because you can go up or down, but I guess that's not necessarily needed. So when referring to the table, this would indicate that the resistor has a resistance of 22,000 ohms with a tolerance of plus or minus 4,400 ohms. So if we were to have a ohm meter on us, that resistor could range anywhere from 17,600 ohms all the way up to 26,400 ohms. The maximum allowable power dissipation or power rating is typically specified for commercial resistors. An important property of the resistor is its ability to convert energy from electrical form into heat. The manufacturer of a resistor generally states the maximum power dissipation allowed for the component, with the units measured in watts. If more power than the resistor is rated for is applied to the component, the resistor would be damaged due to overheating. The instantaneous power by the resistor is given by the following formulas, where V is the voltage drop across the resistance and I is the current through the resistance. And you could expand that even further by using the previously introduced Ohm's law. When introducing that, you can get current squared times the resistance, which is equivalent to the voltage squared divided by the resistance, which is equivalent to the voltage squared multiplied by the conductance. Now let's start transitioning into understanding how resistors behave when they're in wire diagrams and circuits. So here we have two resistors connected together in series, R1 and R2. And for the two resistors in series, they share the voltage, which is in direct proportional to their values, while the same current, I, flows through both of them. Using Ohm's law, the voltage across the circuit can be calculated by taking the current multiplied by the equivalent resistance of the series circuit, which is the sum of the resistors R1 and R2. So you can really simplify this diagram by just combining R1 and R2 by summing them together. Now we have two resistors connected together in parallel. So we have R1 and R2, and for the two resistors in parallel, they actually share the current and is inversely proportional to their values, while the same voltage flows through both channels. And we can utilize Ohm's law again, where the current across the circuit can be calculated by taking the voltage divided by the equivalent resistance of the parallel circuit. And the equivalent resistance is determined by taking the reciprocal of each resistor, and then once you have that, you can sum them all together, and once you have that summed, you can then inverse that value, and that would get you the equivalent resistance, and that would be plugged into the Ohm's law to allow you to determine what the current is in this formula. Alright, you made it to the end, so if you found this lesson helpful and learned something new, please consider leaving a like and subscribing for more engineering crash course lessons, and thanks for watching. I'll hope to see you guys in the next lesson.